All right, well, continuing on with the transform class, get the share going. So the transform class has a number of properties. One we've already seen is the position, transform.position. This is its world space position, but we also have the local position, which is its position relative to its parent if it were a child. We have Euler Angles, which is kind of a measure of the orientation. Here, some object has a rotation x, y, and z. Those are the three Euler Angles. And we also have local Euler Angles, which is its angles relative to its parent. Analogous to the vector 3 dot right, we have a transform dot right, which is the vector going out of the right-hand side of our object. We have transform dot up and transform dot forward. These you can see in, if you have the local on the red, green, the red, green, and blue. Lost the game here. We have the rotation, transform.rotation. This is not the Euler angles. This is instead a quaternion, which is a different way of representing the orientation of an object. We will talk about quaternions in detail later. Generally, we don't have to manipulate them, but we have to know what they are. So rotation and Euler angles are slightly different things. We have a local rotation relative to the parent, and there is no dot scale. There's only a dot local scale, a scale relative to the parent. And that's actually because everything in our scene is the child of the world. The world here is 0 to test simple control B. So other properties, there's the parent, finding the parent of an object, or the root, which is all the way at the top level of a tree of children. There's the child count, how many children an object has. And there's world 2 and local 2 world matrix. These are special matrices used to transform points to and from world to local space. We don't need to use these very much. There are a number of methods. We've already seen the translate method, and this comes with 2 overloads. There's a vector 3 form of it, where the first argument is a vector 3 of x, y, and z values, or there's a version with 3 floats, x, y, and z. There's an optional argument here, the space, and by the space is either itself, which is its local space, or the world, which is its world space, or another object's transform. So you could actually translate things relative to some other object, like the camera's main transform. By default, it's self. If omitted, that's the default. So our little simple move B, here's the translate x 0 z, and this is moving in its self space. So the vertical z is the forward movement in the z direction. Z is the forward on our object. We could have used the vector form, where here now I'm translating in the vector 3 forward, that's 0, 0, 1, scaled by time delta time and a speed. And this would work because the default space is self, and so it moves in the z direction of the self space, so it's going to move our object forward. There's also a rotate method. This one also is overloaded to take either a vector of Euler angles or three floats of their x, y, and z angles. And it too has a relative to space that defines what the movement is relative to. And that there's an analogous rotate around function that rotates about an axis, the second argument defined by a vector 3, that goes through a point, also defined by a vector 3, by an angle defined by a float. So those are two rotate functions. So moving on to simple move C, I've added another float, the rotation speed. I have forward speed and rotation speed now. The horizontal axis, I'm going to scale by my rotation speed. Left and right arrows are going to turn my character. And I'm, of course, scaling it by time delta time so that it moves at a uniform rate. And S is going to be the vertical axis scaled by forward speed and the time delta time. I'm going to translate with S, that's the vertical axis scaled appropriately, times the vector forward, and vector 3 forward. And as I mentioned, because it's the self space, that's going to push my character forward and along its axis. And here I'm going to rotate about the y-axis by RT. So let's see this one look. And here I've made my character a little longer now. So when I press the up arrow key, I move forward, and the down arrow key, I move backwards, and the right and left arrow keys rotate. And because axes can press more than one key at the same time, I can simultaneously turn and move forward and turn at the same time. So all very cool. Another transform function that we encountered back when we were playing with lerps and we had the camera look at lerps is the transform.lookat. This one also has two forms, one where the target is a transform. This is an object in the world that we want to look at. And the other is a vector 3 world position. This is an absolute coordinate in the world, an x and y, x, y, and z position in the world. So either of those two. And it's overloaded, it recognizes what case it's gotten based on the argument. It also has an optional world up vector that defines what direction is up in our camera. And by default, this is the y-axis. And we usually can leave that alone unless we're doing something weird with the camera. As I mentioned, this is useful for aligning cameras, a third-person camera that looks at the character. Here's an example of a program, a script follow that has a public variable, a public transform target. I've got a little debugging Boolean here that's by default false, but if it's true, I'm going to draw a line from the target position to the transform position. The transform position is the object that contains this script and the color of that line. And all I do to make my object look at the target is assign to transform.lookat, and the target that I want to look at. So I didn't use this with the camera. Instead, I've got a little light here. I've got a little light, and I've put on it this follow script, and its target is the player, this thing over here. And I'm going to turn debugging on so that we can kind of see this thing debug here. Let me zoom in on the player a little bit. No, I don't know if, let's see if I have the gizmos set. Yeah, the gizmo is turned on here in the game view. If gizmos is turned off, I don't see the gizmos. There's the light gizmo. With gizmos turned off in the game view, you'll only see them in the scene view. So if I play this, my light is going to look at my player here, who is one of these things that moves around with the WAS and D keys or with the arrow keys. There's the line drawn between the transform and its target. And of course, there's the output of the light that shines a little light on the player. So Lookat function, very powerful, turns the z-axis of the transform that is looking at to point towards the target with, by default, the y-axis in the up direction. There's transform direction and transform point. These two transform either vectors, directions, or points, that is coordinates, from local coordinate to world coordinates, and they both return vector 3 values. They also have inverses that transform from world back to local. Here's an example of one of these. I think this actually comes from the documentation. But this is going to apply a force in the right direction on the camera. So we have our camera's transform. We use that transform direction on the vector 3 to the right, the 0 or the 1, 0, 0 vector. This converts it into world space, and we can now add a force in that direction. This will add a force to the camera relative to the x-axis, not of the world, but of the camera. Because we also have the transform.right, a unit vector and world coordinates in the transform's x direction. So I can actually do this in kind of slightly more straightforward way. Camera relative cam.right, and then just use that to apply my force. So these transform direction and transform points are not always necessary. Here's an example with transform point. I'm going to instantiate an object 2 meters to the right of the object. And so in this case, I've put the script on the player. The position is vector 3 right times 2 transformed into world space, and I'm going to instantiate whatever the object is at that position with my transform's rotation. And so if I look at that one, don't say it. If I look at that one, I believe the P key instantiates it to the right of my object. As I drive around here, I'm dropping it off to the right each time I go. And it's just a little particle effect with a residual. So very cool. Here's the alternative using transform.right. In this case, the position is my position plus 2 times my transform to the right. So this is definitely a little simpler than using this transform point routine. And I highly recommend using this format. There's an isChildOf function in the transform class. The argument is a transform in the world, and you test to see whether the transform that you're on is a child of that object. Returns a Boolean true or false. If it's a child, a deep child, that is a child of a child, or if it's identical to the transform. Otherwise, it's false. And I'm going to pause again here, and I'll pick up next time with accessing components. So I'll stop sharing, and I'm going to end recording, and I'll see you in class. Bye.